All right, it's probably time to start. Welcome, everybody. It's a great pleasure to have today Alan Knutson speaking on geometry of individual terms in the Duistermaat-Heckman formula. Alan, I give you the floor.
Thanks for having me. I'm glad to get a chance to talk about this stuff. So let's recall Duistermaat-Heckman and what I mean by the terms in Duistermaat-Heckman. So what Duistermaat and Heckman were thinking about was a torus acting on a symplectic manifold and with a moment map taking values in the dual Lie algebra. And what was already known at the time of their theorem was that, so the Guillemin-Sternberg theorem was that, let's take this be compact for right now, was that the image of the moment map is a polytope. And what happens in Duistermaat-Heckman is they say, let's not just think about which points in T dual are in the image of this map, but given a point in T dual, what do you get as the symplectic reduction? How is that space varying as you vary the point? So this is telling you about whether the fiber is empty or not empty. But when it's not empty, then you should be asking so many more things about it. So let me say various things, various ways you might compute the thing that they compute. So so definition one is I will make this function from T dual to the reals, where lambda will map to, I take n, I take the symplectic reduction at the point lambda, and I consider the volume of that. And this is pretty much, so this is now a function on the, it's a function on little t dual. When lambda is not in the moment polytope, this reduction is empty, the volume is 0. And this is maybe the best version of the several I'm going to write down, but not the best for computing. But one thing this suggests to you is that you shouldn't just think about the volume of this. You should think about actually what this guy looks like as a symplectic manifold. And the answer is, as you vary lambda a little bit within regions of regular values, then the manifold will not change, only the symplectic form will change. And that's actually what's in the title of the Duistermaat-Heckman paper about, it's something close to on the variation of the symplectic form on the reduced phase space. So what they prove is that as long as lambda is changing within a region of regular values, that the symplectic form on the quotient is changing linearly. And the volume is computed as integrating a certain power of that symplectic form, the top power. So that would say that the volume is changing polynomially. So this is already enough to tell you that this function is going to be piecewise polynomial. Definition two.
Alan, can I just interrupt you quickly? So just to let you know, the ceiling lamp creates a huge washout spot. Yeah, that might be better, or you could just avoid that spot. So basically, exactly the spot where you wrote m omega, that's the blob which you could avoid if you have the lamp on. So some people just ask me to tell you maybe not to write. But now I think, I think now it's good.
But at least we see all the formulas, right?
Yeah.
Everything's good now?
So I don't know what people prefer. Maybe carry on. Maybe you can carry on like this, and then if people complain, then we'll bother you again.
Perfect.
Okay, sorry. Thanks.
So definition two would be, instead of computing the volume after we pushed forward m to T dual, we think about the volume up on the manifold. So we take omega. I didn't give this guy a dimension. It'll be 2n. We take omega to the nth power, and that defines a volume form, but I want to take the associated measure. And for conventionally, this is divided by n factorial. and we take, so this is now a measure on M, and measure is pushed forward. So we take phi lower t and we push forward that measure. And the difference between this story and that one is that this is a measure and this is a function, and you get from here to there by multiplying by a Lebesgue measure. As long as the torus is acting with, as long as the kernel of the action is zero dimensional, then you can get from here to there by multiplying by a Lebesgue measure. Definition 3 is due to Etienne Bott in their Bold Mathematical Ring cohomology. They say, let's take omega, which is it's a closed two form, but it's not closed with respect to the differential in Cartan's model of equivariant cohomology. So if you want to make it closed there, you need to add a correction term to it. And it's exactly the symplectic, the moment map, or minus the moment map. So this guy I want to now use to get some kind of equivariant volume. And you might think, well, let's raise it to the nth power and divide by n factorial. But it ends up being much nicer to exponentiate it, which wouldn't be, if you were thinking non-equivariantly, there wouldn't be any difference between dealing with this and dealing with that, because eventually you're going to integrate and you'll only see the nth term, and the integration is only sensitive to the parts of things in top degree. So there wouldn't be any difference between exponentiating versus this, but in equivariant cohomology there is, because this is going to contribute not just in degrees up to n, but ever after. So this is this turns out to be much nicer. We take that thing and we integrate it, and this is written is a function on little t. It's that's where the Cartan model of a point lives. It's got integrating over m is about pushing to a point. So now I've got this function on little t, and that one I'm actually going to Fourier transform to get a distribution on little t dual. So these are going to both be measures. This one is good to think about, but it's not quite a measure. You need to multiply by hopefully Lebesgue measure to get to these measures. And there's a fourth one that comes up if m is pre-quantizable, or maybe even quantizable, that I don't think is going to be relevant. So I'll skip that one. So what's nice about this one is that, all right, so I already warned you that part of the theorem here is what Duistermaat-Heckman point out is that this is piecewise polynomial. And what Etienne Bott proved is that that's really just a cohomology statement. It's not something intrinsic to symplectic manifolds. For example, if omega were not a symplectic form, but only pre-symplectic, if it were just a closed two form, but possibly degenerate, then the arguments in Duistermaat-Heckman wouldn't, at least on the face of them, directly apply. Whereas what I'm about to say with what Etienne Bott do, it would. So Etienne Bott say this thing can be written using Etienne Bott Berlin-Verne localization as a sum over the fixed points. And let me just assume that the fixed points are isolated, and I've got finitely many fixed points for convenience. And I sum over those, I take the restriction of this class to that point, and the omega dies when you're restricted to a point because it's a two form and the point doesn't support those, but this guy doesn't. So we get e to the minus bt of the point divided by the product of the weights on the tangent space to the point. So at this step, one would like to pull the Fourier transform past the sum and Fourier transform these term by term. And so there's a bunch of things you're familiar with Fourier transforms. One of them is the linearity. Another is that the Fourier transform of this exponential will get you a delta function. And if I were multiplying by linear factors, then you'd say the Fourier transform of that is is differentiation, but since I'm dividing by them, it feels like you want to say the Fourier transform is integration. Sorry, I haven't figured out how to stop my screen from blanking, so I'll be doing that every 5 minutes. But integration is a suspicious thing to do because it involves adding some constant. So here's how we're going to get into how we're going to compute these sorts of things one by one. I'm going to draw a picture of what goes into this version of Duistermaat-Heckman that I got from Gillen and Lerman and Sternberg. I'm not sure really the origins of this point of view. Let's say I've got, in this example, let's say I'm thinking about the 2 torus acting on CP2. And in this case, the moment polytope is a triangle. And what, if I try to Fourier transform each of these one by one, I'll get delta functions at those points. And then what I'd like to do is take these weights, which are just exactly the directions you see here. This picture is in T dual, and weights live there, and moment polytopes live there. So I want to take these weights and I want to integrate these points in those directions. And I say, so if I take this delta function, I'll get now delta functions along this edge. I take that ray and I integrate it this way, and I get Lebesgue measure inside this sector. And yeah.
Sorry, small technical point. I think with the sound, right, Nikita? Do you know what happens with our sound?
The sound is a truck outside. I guess turning on my microphone isn't going to help me at all, but the sound will be done in another minute or two. But
no. I think you see only when you speak there is some funny. So I think it's something with the mic. But okay.
No. I think
did it start 30 seconds ago?
Yeah, more or less. Yeah, I think it's just it tries
truck.
to compensate for noise, and when you speak,
Yes.
it has to amplify, and so it picks up the noise from outside. So I think there's not much we can do.
Okay. Yeah, then forget it.
So, all right. So the thing that's going to go wrong here, if one's naive, is when we'll take each of these points and each of these directions one wants to integrate in, and when we'll get a term that adds a Lebesgue measure on this sector, plus this one, plus this one. So I'll have this and this and this. And if you add those up, of course, you don't get what you want, which is Lebesgue measure on this triangle. So what you do want is something more like this, where this one contributes positively, and this one, instead of integrating in this direction and back into the triangle, we go out this way and contributes negatively. The issue is this, that 1 over x is negative 1 over minus x. And if you naively say, let's think about integrating this and getting a delta function going in the forward direction, that's not the same as if you take negative a delta function and integrate it in the opposite direction. So the measures know more than the rational functions do. And when you're doing this choice of trying to take a rational function and turn it into a measure by Fourier transform, it's going to involve a choice of whether you go in the x direction or the negative x direction for each one of your weights. So in this case, what I'm going to do is pick this prevailing wind and decide that everybody should be going in that direction. So these guys don't flip, one of those flips, both of these things flip, and so I get a plus and a minus and a plus. All right, so I get finally this sector, and then with this guy subtract, so this guy subtracted off, and then here that's been added and subtracted off, and here it's been subtracted off, but then this guy makes it added again. And that all adds up to the triangle that I want. All right. So what I want to do today is give you a geometric explanation. So this is just sort of and by the way, the truck is gone. I hope it sounds all back to normal now.
The sound has improved, yeah.
Yeah. So what I want to give you today is an interpretation of the individual terms in the Duistermaat-Heckman formula, in this version of the Duistermaat-Heckman formula that's this alternating sum of cones. I want to give you a geometric origin of those. And the thing that just already looks weird is that we know what these directions are in the original polytope. Those directions come from the weights of the torus action on the fixed points, which is also what's happening in the formula here. But once I negate them, then what are those supposed to be? Those aren't weights in the manifold. And what they are is they're weights in the cotangent bundle. So everything's going to eventually end up in the cotangent bundle. All right. So what I'm going to need in order to do that are these things called Chern-Schwartz-MacPherson classes. So let me sneak up on those with this. I'm not going to give you the general picture that Chern and Schwartz and MacPherson were thinking about, but instead this approach to them due to Viktor Ginzburg. And so there's two Viktor Ginzburgs. The one that did the stuff I'm about to tell you now did it in 1986. This is the one at Chicago, not the one at Santa Cruz. And he doesn't usually publish under this transliteration. Usually both of them have a Z here. But the paper I'm talking about is under Viktor Ginzburg with an S. So what he thinks about in this paper is he'll have A lives inside M, locally closed submanifold. And so I'm probably going to take both A and M algebraic over the complex numbers. So I'm not saying that's absolutely necessary for everything that I'm saying, but I'm going to restrict to that. Associated to this, there's this D module of distributions on A. And I'll give examples in a second. So what's this guy? This guy is functions on M mixed with vector fields giving first order differential operators, and then I want to take products of those. So M is going to be some complex manifold, maybe C or CP1. When I say functions on M, I don't want you to think global functions. I want you to think of this sheaf of functions. So on any open set in M, it's reasonable to talk about the functions and the vector fields or products of vector fields. And any single vector field gives me a map from functions to itself, and then I can compose those to get higher order differential operators. And I can multiply those by functions to get other things and take linear combinations and so on. So I get this guy, which is this sheaf of non-commutative algebras over M. And if I have a distribution on A, then I know how to multiply by a function on M. I restrict the function from M to A and scale the distribution. And if I have a vector field on M, then I'll think about it as coming partly in the tangent vectors along A, in which case I'll do differentiation, or I'll think about it as coming transverse to A, in which case I will be raising the degree of my distribution. So for example, if I have, if A is a point inside a line, I'll write down this example in detail in a second, then I'm thinking about delta functions, powers of Dirac delta sitting at A, polynomials in Dirac delta. And differentiating delta gets you delta squared. That's the sense in which this is a module over differential operators. And what I let's write down the three examples that I'm particularly thinking about. Let's take C living in C, and if you want to make so here's my A living inside M. And I'll have this generator of the functions on A pushed into M. So that's, so iota here is the map from A to M, and I'm taking functions on A and pushing them into M. This is a push forward in the category of D modules, and what it gets me is distributions on A. So if I want to think about distributions on C, they came from functions on C. If I want to think about functions on C, then I say, yeah, I know how to make that using 1. I can take 1 and multiply it by functions and get everybody else. Versus if I have 0 living in C, then it's the delta function that's generating that. Versus if I have C cross, so here, the way you generate other distributions from the delta function is you differentiate a bunch, and you get powers of the delta function, and you take combinations of those. So by generator, I mean generator as a module over DM. And then there's C cross living in C, and this one's a little bit more fun. This is the function Z inverse, or maybe X inverse. So if you think about functions on here, you'd say that's C bracket X inverse. And that's certainly a module over C bracket X. But it's an infinitely generated module. You need, if you only use finitely many elements in here, they'll only have negative powers down to some level, and you won't be able to make everything. But if you start with X inverse and you start differentiating it, then you can get all the negative powers. So this is not a finitely generated module over C bracket X. So it's not a finitely generated module over functions on the line, but it is a finitely generated module over differential operators on the line. And this generates. So each of these is some generator for my D module, which means that my D module looks like DM, in this case, DC, and a C, modulo some annihilator. And this suggests if I want to understand these D modules, I should think about what are the simplest things that annihilate these. So the question is, what differential equations do these functions satisfy? So 1 is annihilated by d by dx. Delta is annihilated by multiply by x. So I'm using hat for multiplication operator, not for Fourier transform. X inverse is trickier. you need to first multiply it by x, so it becomes 1, and then you differentiate that. So these guys who are generating my D modules, so my D modules don't look like DC, they look like DC modulo something. And this is telling me what to mod out. DC modulo the right ideal generated by this, or the right ideal generated by that. So let me write down what DC is. DC is this algebra generated by multiplication and differentiation modulo this Heisenberg relation that they satisfy. Okay, that's what the ring of global differential operators on the entire C looks like. We're lucky in this case that C is affine, so I don't have to think in sheaf language. I can just say, what are these global differential operators? Okay, so what we're going to do with these D modules is take their characteristic cycles. So if you think of vector fields as sections of the tangent bundle, then you can equally well think of them as linear functions on the cotangent bundle. And that means that we get two different algebras that vector fields live in. There's this non-commutative algebra in which vector fields don't commute, because what we're doing with them is they're giving us these operators, and those operators don't commute. Versus we have a commutative algebra, which is the functions on the cotangent bundle. Or of course, yes.
Just maybe a naive question. So your previous considerations, they indicate, are we going to work with some kind of Kähler manifolds because you do it over C, or are we going to do it over...
Yeah, I'm taking everything. So for what I'm describing right now, I'm not using a symplectic structure anywhere. So in that sense, I'm going to say no, not Kähler. For the story I'm telling right now, it's just about a manifold and a submanifold, and I would probably prefer them to be algebraic.
Sure, but I was wondering where we're heading, right? We started with a symplectic story, and now it's a story over C. So, like logically, right? It's kind of, or are we going to do it in a smooth category in the end?
And so I am not going to take the trouble to do things in the smooth category. I'm definitely going to the result I'm going to state at the fairly soon. The result I'm going to state is definitely indeed where M will be a smooth projective complex variety. So in particular, it'll be Kähler. And again, I'm not making much attempt to state things in what might be their natural generality. Sure.
Just to be sure, what's the setup? Thanks.
Yeah. So, well, I guess the principal thing that one could be unclear on in terms of what sort of space I'm thinking about here, once I bring in the symplectic structure again, it's going to be a 1-1 form, not a 2-0 form. So if you were worried that I was going to start going holomorphic symplectic on you, I won't. All right, so in this algebra, I've got, I also have vector fields living in here, but they commute. And what the relation between these two is, this guy is filtered. Is filtered by degree. So I've got these first order differential operators, and then I start multiplying them and get second order. And the thing that can happen is that you think you're doing a calculation and getting second order and becomes first order again. If you take the commutator of two first order differential operators, that will in fact be first order again. That's the Lie bracket of vector fields. So this is only a filtered ring, whereas functions on T star M is a graded ring, and this guy is in fact the associated graded of the ring of differential operators. So that's nice because I'd rather think about geometry personally than about differential operators and differential equations. And so that says if I have a differential equation and I'm thinking about the corresponding D module, where I take D modulo the differential equation, you have the D module, then somehow I should be able to get a hold of that as something related to the cotangent bundle. So the statement is, so theorem, this is not mine, there exists a good filtration on these D modules that I was associating to submanifolds. And the goodness of it is that it's compatible with the filtration on the ring of differential operators. So this is a standard thing that improves in a course on D modules, and what it gets you is that this associated graded acts on the associated graded of this. And so the annoyance is that this existence is not unique. So once you've done this, you'll end up with, and so this was functions on the cotangent bundle. Once you've done this, you'll end up with some sheaf living on the cotangent bundle, and it's not well defined. So its support is well defined. Its support with multiplicities is well defined, and so this gives a well defined Lagrangian cycle. And it's better than just a Lagrangian because we have this grading on things. This is somehow graded, well, this is graded. And in fact, what's the grading on here? So when you have a grading on an algebra, that's the same as having an action of the multiplicative group. So you could call it S1 or C cross or something. C cross would be more natural here. Why would I have a C cross action? Because the cotangent bundle has this C cross action where you scale the fibers. So that's what the grading is here. And what it's going to get you here is that this Lagrangian will not be any old Lagrangian inside the cotangent bundle. It'll be what's called a conical Lagrangian, that it is invariant under dilation of the fibers. So that's very restrictive. So if you might feel like there should be a whole lot of Lagrangians, some infinite dimensional space of them, but particularly Lagrangians inside the cotangent bundle, that's got twice the dimension of M. There should be a lot of options there. Once you say you're thinking about a Lagrangian and something conical, if you also say irreducible, then actually such a cycle in the cotangent bundle is determined by its intersection with M. So conical Lagrangian cycles, they're not so different from subvarieties of M. There's somehow the same amount of both. Okay, so let's do that in this case. I have these three different locally closed submanifolds of C, and they're getting me these three different D modules, D modulo this thing. And let's complete this picture to think about the characteristic cycle of this subvariety A that we had here. So the in general, there's a characteristic cycle for D modules. The only D modules that I'm considering in what we're talking about are this special kind of D module. So here, I need a name for the functions on the cotangent bundle, and the traditional name is position and momentum. So this is the one that came from x hat, and this is the one that came from ddx. So ddx is going in the associated gradient is going to get me this q, and so I will end up with q equals 0. So that's the 0 section in the cotangent bundle. Versus this point is getting me p equals 0. So that's getting me this vertical line in the cotangent bundle. So this is, here I had the 0 section in the cotangent bundle. Here I've got the conormal bundle of the point, the cotangent space at the origin. And here I'm getting the union of the two of them. So that seems pretty suggestive, and there's something that's really unpleasant here, which is that on this side you'd say C is 0, disjoint union C cross. So I've got this guy is this guy plus this guy on this side. Here I've got this guy, I've got this is that plus that. So we're going to have to introduce some minus signs if we want to somehow reconcile what's on the left-hand side and what's on the right-hand side. Any questions right now?
Or maybe I think it's P and Q. Q is usually coordinates and P is momentum.
Oh, of course you're right. Yep. All right. Don't need to change that one. Okay. Well, no, that's good. That's it. Okay. All right. So, what Viktor Ginzburg observes is, so his theorem is that if you take the characteristic cycle of A living inside M and you consider that thing as an element in the cohomology of the cotangent bundle, but it's better than, you should do better than that because actually it lives inside the dilation equivariant cohomology of the cotangent bundle if you'd like, because it was a conical Lagrangian. And let me point out, this is kind of silly, right? This thing retracts to M, and once it retracts, so this is the same as this. Once you retract to M, then the C cross actions become trivial. And so this is just the ordinary cohomology of M, bracket some new variable I'll call H bar. So this thing is living in ordinary cohomology with some new variable attached. And what we've seen is that if we'd like the disjoint union story here to match up well with what we're seeing in the characteristic cycles, we want to multiply this by the codimension of A. So that would give us a plus for this guy and a minus for this guy and a plus for that guy. And it says that the one at the top is the one at the bottom minus the one in the middle. Excuse me. No, this would say this guy should be the sum of these two. And now this thing is indeed the sum of these two. So I haven't stated a theorem here yet. The theorem is that this is the Chern-Schwartz-MacPherson class associated to A. And I'm not going to define those, but I'll tell you what the corollary is in a second. So that's not quite right because This guy traditionally is an inhomogeneous homology class instead of this thing, which is a perfectly nice cohomology class. So in order to actually get from here to there, you need to do this stupid thing of setting h bar equal to a constant, dehomogenizing this. And I think it's ridiculous to ever talk about an inhomogeneous homology class or inhomogeneous cohomology class, because homology and cohomology should be arriving from as the associated grade of K theory. And you can never take an ungraded element and ask, how could I lift this to being an honest element of K theory? So I think it's already just weird to talk about this inhomogeneous thing. But this is just there for sort of historical purposes. I'm telling you the thing that makes sense geometrically and not the original way it was described. And there's one other issue, which is that this is in homology instead of cohomology. So it's also supposed to cap with the fundamental class. But all this is to say, the corollary, which is the important property that Chern-Schwartz-MacPherson classes have. So without telling you what Chern-Schwartz-MacPherson classes have, I'll tell you this. If B is inside A is inside M, so this is still this locally closed story that we were talking about. And this guy I'm going to have actually be closed, okay? Then, or sorry, maybe I'll say this as this fact about CSM classes. The only thing you really need to know about them today.
B closed in M or B closed in A?
A. B closed in A. Okay. So if we have that, then we can associate this CSM class to A, and we can associate a CSM class to B, because B is locally closed in M. And we can also associate one to A with B removed. Is that still on the board, or is that too far to the right? I think it's just barely okay.
Yeah, we can see it, but yeah, okay.
So one has this additivity of CSM classes, which was the additivity we were seeing in this example. And what the CSM people do is they think about associating a class not just to locally closed submanifolds, but to linear combinations of those. So they think about it as something where a constructible function goes in and a homology class comes out. And if you want that to be a reasonable definition, then when you write your constructible function, like 1 sub A, as a linear combination of other constructible functions, you're going to need your recipe to be linear, and that's what the CSM classes magically do. So Ginsburg verifies that these geometrically constructed classes have that additivity property. Okay, so back to Duistermaat-Heckman. So in the Duistermaat-Heckman story, what we have was we had this torus acting on M. We had this moment map. And you remember that I had this prevailing wind X, which lives in little t. So And that guy X is not perpendicular to any isotropy weight. So given any isotropy weight, we flip it to be positive with respect to X.
Alan?
Yeah, I should stop using the red.
For some reason, I now have a difficulty to see your writing. I don't know whether it's the pen or whether it's a light.
Yeah, I'll stop using that red. So I've got this X in T. Is good?
Oh, that's good.
Okay.
That's
X is not perpendicular to any isotropy weight. So one way to say that is if you dot with X, so you go from T dual to the reals, then this composite should be Morse. Now that I have a Morse decomposition, now that I have a Morse function, I'll make a Morse decomposition. M will be the disjoint union over F in the fixed points of the Morse stratum. Okay. So what is it that I want to compute? I'm thinking about the Duistermaat-Heckman function or Duistermaat-Heckman measure associated to M. And I'm, let me put this T here, and I'm going to include this extra circle action, the stupid one that didn't act on M at all, but will act on the cotangent bundle. So this is what we want to compute. And I say, well, that's the Fourier transform of the integral of e to the over m of e to the omega minus phi, as we said. Now I'm going to do that computation not on the manifold itself, but on the cotangent bundle. So you can worry about what integration on the cotangent bundle means. I'm going to say, let's just define it from the equivariant localization formula. So I'm mostly doing algebra here, not any serious analysis about integration over non-compact space. So I've still got this e to the omega minus phi, but now I need to include the class of the zero section. So I'm using the push-pull formula here about either I go from M down to a point, or I go from M into the cotangent bundle, and then I go from there down to a point. Okay. That guy, this thing, this zero section, we saw that happening in this example here. That is the CSM class of M living inside M. If you think about M inside M and you associate the characteristic cycle, you get the zero section. So this thing right here is the CSM class of M itself. Okay, now I'm going to use this a whole bunch of times to say, if you have a disjoint decomposition, then the CSM classes add up. So this is going to be Fourier transform, integral over the cotangent bundle. This guy's along for the ride. But that thing has now become this sum over the fixed points of the CSM classes of the Morse strata. Okay, so that's where I use the additivity of CSM classes. And honestly, I don't really want the CSM class. What I want is this thing that lives on the cotangent bundle. So maybe this homogenized CSM class where you stick the H bars back in where they always should have been. Okay. So this, I would like to say, we're going to do this this interchanging Fourier transform and summation thing. So I'll get this sum over f and mt of this integral over the cotangent bundle of e to the omega minus phi. But now this guy, I'm going to plug in the formula we had for CSM classes, Ginsburg's formula. So there I'll get a -1 to the codimension of A. So A in this question is this Morse stratum. So I'm getting a -1 to the index of F. And then I'm getting the characteristic cycle of the Morse stratum. And there's still a Fourier transform. Now I'm going to do push-pull again and say, instead of integrating over the cotangent bundle, let's, and then inside there, multiply by this class of this characteristic cycle. This is going to be sum over the fixed points. I've got this -1 to the index of F. And I've got the Duistermaat-Heckman, the Duistermaat-Heckman measure of the characteristic cycle. All right, let's do an example. So let's take CP1, whose Duistermaat-Heckman measure looks like this, right? With the circle acting on CP1, and usually you would say that's equal to this guy plus that minus that. That would be the alternating sum of cones thing. All right, so I'm saying instead of computing this inside CP1, let's think about the cotangent bundle. So what I have here is the cotangent bundle of CP1. And so this guy is, in this tiny example, this guy is also a toric variety. It's got two circles, the one that we had from the beginning that was acting on the CP1, and another one which is the one dilating the fibers of the cotangent bundle. Okay. And we're trying to compute this measure. So if I thought about the Duistermaat-Heckman measure of the entire cotangent bundle, it would live on this, this sort of infinite trapezoid. But I only want it for the CP1, so I just have this guy living inside. Okay. So this thing, the Morse decomposition of this is into this C and this point. And we thought about what's happening. So if you want to think about the characteristic cycle of these two, we can think about it at this end or at that end. And the characteristic cycle of the point is just going to be the cotangent fiber. So that's the cotangent fiber at that point to the CP1. The characteristic cycle of the C is more complicated. So at this end, it just looks like C inside C, and we say, yeah, it just looks like the zero section. But at the other end, it looks like the calculation we did on the board before, where we had C cross inside C, and its characteristic cycle had two components, the zero section and the cotangent fiber. So actually, this characteristic cycle has these two components. And the formula that I have written here would be that I can compute this as this guy minus that guy. And the minus is coming from the codimension of this point, right? That it's this minus here, -1 to the codimension of the stratum. So I get this weird looking formula. The thing that I want is equal to this bent thing minus that. And that's a little bit richer than the formula that you expect to see in Duistermaat-Heckman. So what happens is you take this and say, well, I never really cared about the extra circle action that was on the cotangent directions. So I'm going to take this, I'm going to project it to the line, I'm going to flatten it. And then these two things, this falls over, and you no longer see this bend. And this guy turns into that half line, whereas this guy turns into negative that half line. So the final ingredient is this theorem of André Weber, which is if you have a point in M that is not in A, and you consider the CSM equivariant CSM class associated to A, then the restriction of the class to that point will be a multiple of H bar. So the way we got from this picture to that one was by setting H bar to 0, that we're forgetting the dilation action. So that's the sense in which this bend will smooth itself out and we won't see it. And each of the terms that we have here will turn into the terms in the usual Duistermaat-Heckman. All right, I should stop there.
Thanks a lot, Alan. Well, please, questions or comments? You can either unmute yourself or raise your electronic hand.
Hi, I have a question. Thank you for the talk. So some of the ingredients that you introduced here also have a more like functional analytic side. For example, in microlocal analysis, where you get these Lagrangians as wavefronts of certain functions and so on. Do you know if there is an analogous explanation of these individual terms also in that setting, more analytic?
I mean, I think it's going to be largely the same and just a question of language. In both situations, what we're talking about is PDEs, right? So here instead of talking about PDEs directly, I talked about D modules, but D modules is just what you do in a D module is you think about what the differential equation is without thinking about actually trying to solve it somewhere, right? Like algebraists can't solve the differential equation y prime equals y because it's not a polynomial, but instead they'll say, let's consider the ring of differential operators modulo of the ideal ddx minus 1, and that's a module. So they don't care about them trying to morph that module into some space of functions where it might find a solution. But regardless, still the fundamental thing that both people are thinking about is solutions to differential equations and then trying to do something. So I said I was using this language of associated graded giving characteristic cycles, and the words that I hear from microlocal people are maybe more towards principal symbol and such. But I don't think that there's I think it's more a matter of translation, and I'm not going to say I'm competent to perform that translation, but I don't think that the ideas are too different.
Okay, thank you.
Thank you. More questions or comments?
Yes, so I have a question. So
Yeah, please go.
Yes, so if I understand for your, what is the restriction of the fixed points? It's a function on two variables on the fixed points. These cycles, they give, these characteristic classes gives a polynomial function on two variables. Is that correct?
Well, when I restrict to fixed points,
yes, can you describe the restriction of the two fixed points of these two cycles? You have two things. You have a formula with, so I suppose, I didn't understood what the formula of Weber was saying. It was saying something that it was divisible by something?
Right. So the point is this. The point is this. I'll have this characteristic cycle, and I restrict it to a point, and that will live in not just T equivariant.
So it's just a function of two variables. So
no, it's not two variables. It's, I mean, in the example I wrote down, T is one-dimensional, but in general.
Okay, no, I want this example, just this example.
Okay. Well, so here, so in particularly in this example, then this guy,
yes, this is usual. So okay, so we don't.
H bar minus H bar
there
minus
is
X
no action.
and H bar plus X.
Okay.
Here it's H bar minus X, and here it's H bar, and here it's 0 and minus X.
So what is the theorem of Weber that you see there?
This.
You said something. You said that.
So what he proves is if P is not in A, inside our guy M, then when you take the characteristic cycle associated to A and you restrict it to the point P, then that will be congruent to 0 mod H bar.
Okay, so this is this. Okay.
So that's it. So the question of what are these actually equal to? I cannot compute those, and I don't do that.
Because it's okay. So
similarities that's happening around the boundary of a Morse string. So I'm not computing those. I only compute them in at the point F itself, where that's where of course the thing is smooth and it's easy. And at all the other points, I get to use this to say once I set H bar to 0, then I don't have to compute those.
So it's very similar to the stable envelope. Is that correct?
Absolutely. So in the case, so the stable envelope story is a little bit more restrictive, but yes. So stable envelopes. So if stable envelopes are defined for symplectic resolutions more generally, but if your symplectic resolution is a cotangent level, then the stable envelopes will exactly be the characteristic cycles of the Morse strata in the base.
And so I know I didn't understood what was the restriction of because it was needing to be so stable envelopes you are saying is not exact. Is this in the special case?
No, I'm saying the definition of stable envelope is more general. It's about symplectic resolutions. In the case that we have here, that the variety we're thinking about is a cotangent funnel, then the stable envelopes will indeed be these the classes of these characteristic cycles. So exactly on the nose. And the difference being, of course, that traditionally with the stable envelope thing, you define them in part using this condition.
Yes, this is what I understood from stable envelopes. You compute them using this.
Right.
This,
so here it's the opposite. Here we're defining them from the Ginsburg thing, and then saying, but Weber says that they satisfy this. So this is a theorem where here the input was the characteristic cycles, and Weber has a theorem about them, rather than the input being this condition and the output being the stable envelopes.
Okay. Thank you.
More questions? Yeah, more questions or comments? maybe I have a follow-up question for Michelle's question. Maybe I don't quite understand notation. What if you don't do the Fourier transform? If you only just consider those Duistermaat-Heckman integrals, right? So you say there should be a formula now with two variables, right? H and X.
Dimension of t plus one variables.
Yeah. Okay, but let's say we're still doing this CP1. What's the formula? What's the formula for the Duistermaat-Heckman integral with two variables? Could you just for CP1? Could you spell it out? Just I think that probably would help me to see, right? Usually we have this sine divided by x is equal to, or sine hyperbolic equal to the difference of two exponentials divided by x. But now there is also an h upgrade. So how would it look like?
Yes. So so let me call these. I'll call the images of the moment map k and negative k. So that's where these positions are. And so so for CP1 itself, we get e to the minus k divided by h bar minus x. E to the minus kx maybe. And plus e to the k over h bar plus x.
Sorry, it shouldn't be e to the power minus kx or something, right? Or I don't know, or h minus x. Or...
Yeah, I think you're right. I need this x there. So that's what I had. So this is here's the sum over the fixed points, and in each of the fixed points I have this denominator that involves this this h bar. So and then this one I'm going to get well that same thing. So it's going to be easiest for me to do that. I mean, I'll tell you exactly what that is. It's that same thing plus this term, which I'm about to subtract off again. So plus e to the kx over h bar. So that's what I'm going to get here, and then I'm going to be subtracting off this e to the kx over. Sorry, I said h bar. No, I don't mean that. I mean minus x, and here it's going to be over minus x.
Okay, can I say something?
Yep.
Because I think if you go characteristic cycles, then you should have the wavefront sets that you could see from the characteristic cycle from the image of the when you have you should know a little bit better what is this x below, because you should know the wavefront set of the Fourier transform. No. Anyway, so I want to say, e power hx over x, you have to say something more. You have to say which direction you take the Fourier transform. And I think it's somewhat you can see it. I think it's nice. It's very nice. I kind of see it. I don't know.
So are you coming back to the issue of 1 over x versus negative 1 over minus x?
Yes, that's right.
Okay.
And I claim that somewhat it should be dictated because you should see the wavefront set.
Yeah, so this is so I would say this is what's hiding here. That where I said now that I want a Fourier transform term by term, I'm going to run into those sorts of issues. What I would like to say, so two things. What I would like to say is that that as long as I know which direction I want my individual my measures to be supported in, and so that's going to tell me how to do these calculations one by one. That's fine, but then it's not clear that when I take them and I project them, I project out the h-bar direction, that I get the measures that one sees exactly in the Duistermaat-Heckman formula, or the Gilman-Sternberg version of it. One thing that has worried me in trying to generalize this, because the principal thing that I used here was this decomposition, and then I applied the CSM thing to that to say CSM of this is the sum of the CSMs of that. And you can imagine doing that with other decompositions. So in the paper, I say about doing it with the decomposition of toric variety into torus orbits and getting the Briand-Schön-Graham formula. There are other examples that that definitely work out less well with this in terms of which directions you should be going. But it's getting late. They're spelled out at the end of my recent paper on the archive.
Okay, thanks a lot. More questions or comments? I perhaps have one more somewhat naive question. So now you're saying that if I can try to summarize that those localization contributions, they have an upgrade with one more parameter, right?
Yeah.
And even in this CP1 example,
they're nasty.
One of those upgrades, right? It looks like a linear combination of three exponentials with different denominators, and it looks kind of tricky, right? The first one, the one which is same plus the other exponential. Does this thing satisfy some equation, or does it have some beautiful property?
I was putting in normal directions here, and I should have been putting in tangent directions. So I should have the tangent directions here. Sorry.
Okay.
Try that one more time.
Okay. Yeah, let's do it one. So it's
of the classes to points. So but those are the classes inside the, as defined on the ambient cotangent bundle.
Mm-hmm.
I was mixing up normal and tangent directions. So here we're going to get that same thing.
So you don't modify the answer, no H's anymore, right?
Yeah, you will not modify the answer.
Okay, fine.
No, it's just there will be these H bars floating around in the individual terms.
Yes, good.
So with this one, we'll get e to the kx over H bar plus x, and then we'll be subtracting that off.
Okay, perfect, fine. Still, so there is this. There are those two terms, but do they have some properties, right? You can kind of say satisfy, I don't know, some differential or difference equation or something.
Oh,
could you give an example? So now this
yes,
first
there's a big story in which Michel alludes to about stable envelopes, and I guess the tiny thing I want to say about it is that if you do this on a flag manifold, where normally you would just do the Morse decomposition of your flag manifold into Bruhat cells, and they would give you these classes, and those classes would be related by these divided difference operators. And divided difference operators square to 0. So they mostly, they commute, they braid like they're supposed to, but also they square to 0. These ones are better in the sense that they're related not by the divided difference operators, but by reflection plus H bar times the divided difference operator. So these guys, again, commute and braid like you expect, but they square to 1. So that's somehow less nilpotent than the thing you're used to on the manifold itself. And you can recover what's happening on the manifold itself by taking this h bar to infinity limit. And so the stuff I was doing here was setting h bar to 0, and things became really, really stupid, where this guy was only supported at one point, and this one, you couldn't even feel this point anymore. So that's the h bar to 0 limits that I was using. But here, h bar to infinity is what picks out just the partial I term and gets you back down to thinking about Schubert classes on the base instead of these more interesting Molokov stable classes on the cotangent bundle. So maybe that's the sort of operator theoretic thing you want to do here.
But h to infinity doesn't look like a very good limit, right, in your formulas with exponentials. So things will gonna just die, right, there, or what?
Basically, the h to infinity, I mean, of course you need to normalize things, right? You need to take your classes and multiply by power of h before you do this limit. But once you do that, then the limit of the stable classes with these proper powers becomes the Schubert classes.
Okay.
So
okay.
they are quite seriously an upgrade of the Schubert classes.
Okay. Thanks a lot. So more questions or comments? Look, if not, Alan, thanks a lot. So yeah, thanks a lot to all participants, and Alan, thank you again for a great talk.
Thanks.
So let me remind you that next week, so there are two things which happen to the schedule, right? We are on the Eastern Hemisphere schedule on the one hand, and on the other hand, typically our reference time is related to the Europe time, and Europe changes to summertime. So in the end, I don't know, Nikita, do you know it shifts by 3 hours, or it shifts by 4 hours, by 2 hours? So it's some kind of, probably, Nikita, you need to send us some instructions for the next week, right? Because it's Eastern Hemisphere time, and also Europe has a different time. So for people in other time zones, it will be some kind of relatively unpredictable change.
Well, yeah,
right?
In the emails, usually there's several time zones that are listed. So hopefully that should be enough.
Okay, that's a very optimistic view of things, but yeah, let's